Let's talk about the kinematic equations for constant acceleration. What we're going to do is develop a list of equations that will allow us to solve problems that involve situations where the acceleration is constant throughout a given time interval that we're looking at. And these have a lot of practical applications. For example, if you drop a rock off a cliff and you time it, you can figure out, how high the cliff is and how fast the rock is going when it hits the ground, all kinds of stuff like that. So they're pretty useful things. But first I do want to review a little bit of what we've been doing with graphs. I'm really big on graphs. I think being able to interpret graphs is a hugely important skill. So we have a situation like this, and I'm going to leave some space above here. I'm going to draw a velocity versus time graph. Okay, and so I've got a situation where my velocity, let's say I have some starting velocity that isn't zero, and I increase that velocity at a steady rate. Okay. Now, if I want to draw a position versus time graph based on this, well, first of all, I can describe this with an equation, right? I can say my final velocity will be equal to my initial velocity, or the velocity that I'm starting at. My starting velocity, my velocity when t is equal to 0, plus, here's v naught right here, plus my acceleration times time. Now we've already done this, right? This is just the straight line equation for velocity. Remember, we can say y equals mx plus b, right? This is a straight line, but instead of y, we have v. M is the slope. Well, what is m? That's delta v over delta t. Okay, but we call that acceleration. And then my horizontal axis, instead of calling it x, we call it t, plus my my y-intercept, but we're calling that v naught. Now, for reasons that kind of make sense, that do make sense, just trust me on this, it makes sense. It doesn't really matter, but they change the order here. We switch the order here. We have v naught plus at as we just switch the order of these. And this right here is my first kinematic equation. Okay? Well, now, remember that, let me zoom out. I'm going to do it a little differently. Now, do recall that we said that the area underneath this graph represents my displacement. So now what I want to do is develop some equations that describe displacement. And so let me redraw this because I cluttered it up with all that stuff. So here's my velocity and here's time. And I'm going to assume again that here's my initial velocity v, and I'm going to increase that velocity. It would work if I decreased it, by the way. It just looks a little different. As a function for a certain time interval. Now let's say here's my final time right here. And I want to know, okay, what is my displacement? How much did I change my position if I did this? Well, we've said a dozen times now that displacement is in this graph, right? It's the area underneath the graph, right? So I'm going to figure out the area underneath this graph. Now let me show you a trick for figuring out the area. Well, there are two ways to solve the area underneath this graph. I can divide it into a rectangle and a triangle, right? And add them together. Does that make sense? Right, here's my rectangle. This is my displacement because I had initial velocity. And this is my displacement because I increased that initial velocity. I mean, I increased from there. I went faster and faster and faster, so I went farther. But can anybody take a look at this? Remember from geometry? Rather than adding a rectangle and a triangle, I can go right to the answer with one equation. I can figure out the area of this without having to add anything, like adding two different areas. What is this shape? Ooh, these two sides are parallel. These two sides are not parallel. What do we call a four-sided shape where two opposite sides are parallel and the other two sides aren't? Did that question make you feel trapped? Yeah, that was a hint. It's a trapezoid, right? Do you remember the equation for the area of a trapezoid? No, I don't either. Well, yeah, I do, because I teach this every year, so I remember. All right. It's the average base times the height. Wait a minute. What? Turn it like this. This is why I like doing this with a document camera, because when I was doing this on whiteboards, I had to make the kids all turn their heads sideways. But I don't have to do that anymore. Look, this is a trapezoid, right? So it's the average base. Here's base 1. Here's base 2. Times the height. Here's the height. Now, we need to name this base. So this is going to be the final velocity. So we'll bring that over here. And so this is the final velocity. And this time t, we'll call this our final time t. This is the height. So what you learn in geometry is that the area of a trapezoid is the average, the arithmetic average of the base times the height. So what is that? Well, the area of this is delta x. Right? We said this is delta x. That's the area underneath the velocity versus time graph is my displacement. Well, how do I find the average base? Well, it's the first base plus the second base, right, divided by 2. And then we have to multiply by the height. Okay, what's the height from here to here? That is the time interval we're looking at. That's t. And there we go. This is the second kinematic equation that we're going to use to solve problems involving constant acceleration. And this really does assume constant acceleration. This equation does not work if your acceleration is not constant, because if the acceleration wasn't constant, this shape would not be a trapezoid, would it? If the acceleration increased with time, my velocity would increase with time, and that would make some kind of a curve. Okay? So if the acceleration is constant, though, this will be a straight line. And therefore you have a trapezoid, and therefore this equation will work, because it's the area of a trapezoid. Now, I will also argue now that this v naught plus v divided by 2, where is that on here? Well, here's v naught. Let's say v naught was 2 meters per second. And let's say this was 6 meters per second. So where would this be, right in between them? It would be 4. Do you see it would be 4? Now you can also get that by going 2 v naught plus 6 divided by 2 is 4. Right? That's the average, that's the value of a velocity that's exactly in between v naught and v. So that would be right here, right in between them. And so if I draw a line across like this, here's what I want you to see. I can take this triangle and flip it over and put it in here, and now what have I got? A rectangle. And so now I could say, oh, it's just 4 meters per second times 5 seconds, whatever I'm using, and I can get my total displacement. Really what I just did is I derived the formula for the area of a trapezoid. Okay? But sometimes in physics, we have to just kind of take the results we learn in math and just go with them. Okay, yeah, the mathematicians proved that. I believe them, so I'm just going to use it. But you can also see it. If I cut this out with scissors and put it over there, I've now got a rectangle. So it's just going to be this height, which is this plus this divided by 2, times this length, which is time. Voila, I got my equation for displacement. Okay. Everybody good? Next. Let's redraw that. V and t again. Here's our starting velocity, and we have a constant acceleration. Okay, for a certain time. Now, I'm going to come up with another equation for the displacement. This time I am going to break it up into a rectangle and a triangle. So I'll call this, delta x1 and this delta x2. Here's the area of the rectangle. Here's the area of the triangle. Well, let's come up with an equation for the area of the rectangle. Well, the rectangle would be delta x1 here would be equal to, well, it's just a rectangle, so it's base times height, right? So it's just going to be this height, v naught, times this t, and this is how far I go because I had starting velocity. Okay, I mean, if I didn't increase my velocity, if I just stayed at v naught the whole time, it'd be just like unit 1, and that would be how much I changed my position. Now, delta x2 is a little bit interesting. It's a triangle, right? So it's 1/2 the base. Well, what's the base? I'll call this delta x2 equals 1/2 the base is time, right? Times the what? The height of the triangle. Well, what is this height? Using these variables, here's my final velocity up here again. This is delta v, isn't it? My change of velocity over this entire time interval, which is equal to my final velocity minus my initial velocity. Isn't that the height here? Do you see that? So this is going to be, this delta x2 is going to be 1/2 the base times the height. So this is going to be v minus v naught. Now I'm going to do a little mathematical substitution, okay, to make this a little bit better. Here's the equation I started off with, the equation of the straight line. And what I'm going to do is I'm going to take this equation, v equals v naught plus at, and I'm going to subtract v naught from both sides. So what do I get? v minus v naught, that's my change in velocity, is equal to acceleration times time. So my change in velocity is equal to acceleration times time. So now I can substitute this a times t, the acceleration times time, in for v minus v naught in my equation. 1/2 t, 1/2 the base times the height. But now the height here, I can consider this to be a times t. Well, this is pretty screwy looking. So I'm going to call that t times t is t squared. So it's 1/2 the acceleration times time squared. So this is this gives me the area underneath the triangle expressed in terms of time and acceleration. Now I have to add these two together, delta x1 and delta x2, to get my total delta x. So I can say delta x is equal to delta x1, the area of the rectangle, plus the area of the triangle, 1/2 at squared. And this gives me my third kinematic equation. I'm going to derive one more. And this one is strictly going to be a mathematical, an algebraic one. I'm not going to use, look, let me zoom out so you can see the whole page here. All of these three equations are all based on this graph, velocity increasing at a steady rate with time. So this is an object going faster and faster and faster and faster. And we came up with this equation for velocity. It's just a straight line equation. Then we said, oh, the area underneath this graph is our displacement, and it makes a trapezoid. So that gives me this second equation. And then this, I've got a rectangle and a triangle. If I add them together, I get this third kinematic equation. Now, you'll see why I'm developing these four. I'm going to develop a fourth and final equation, and I'm going to show you why I'm developing those. So trust me, there's a method to all this madness. Here's what I'm going to do now. And I'm going to solve the first equation for time and substitute it in here into this equation, and then I'm going to clean it up. Okay, here's what I'm trying to do. I'm trying to develop a set of equations where something different is missing in each equation. Like in this equation, there's no delta x. In this equation, there's no acceleration. In this equation, there's no final velocity. And in the equation I'm about to develop, there will be no time. And this turns out to be very useful. Okay, and you'll see here in a minute. So I'm going to take this equation, v equals v naught plus at, and I'm going to solve it for time. So a times t equals v minus v naught. And this is, hey, by the way, a times t, what is that? That's the area underneath an acceleration versus time graph for constant acceleration. It makes a rectangle, and the area underneath an acceleration versus time graph is just my change in velocity, which is final minus initial velocity. So that's what we did before. Woohoo! Now, to solve for time, I'm going to divide both sides by acceleration. Okay? And there we go. Now I'm going to take this value for time, and I'm going to substitute it in there. The rules of algebra say that's fine. You can always make a substitution. So I'm going to have delta x equals my starting velocity plus my final velocity over 2. Let me erase that. That looks clean. Times time. Okay, well, time is down here, so I'm going to say v minus v naught over a. Now, this is kind of messy, so I'm just going to start cleaning it up. And it's just algebra, and it's kind of arbitrarily, we're going to choose a place to stop kind of arbitrarily. But so delta x is equal to, well, let's FOIL this thing. So we've got v naught v minus v naught squared plus v squared minus v naught. Okay, I just multiplied this times this, this times this, this times this, this times this, all over 2a. Yes, you all agree? Okay. Now, anything go away? Yes, think. Look at the equation carefully. Look in that numerator. Something will go away because I'm adding and subtracting the same thing. So therefore, what is 2 minus 2? 0. V naught times v is the same as v times v naught, isn't it? And here I'm adding it, and here I'm subtracting it, so they go away. And I don't like the order of this, so I'm going to change this. I could stop there, and I would, because now everything is solved for delta x. But every textbook I've ever seen keeps going a little bit. Let's multiply both sides by 2a. So I get 2a delta x equals v squared minus v naught squared. Now let's add v naught squared to both sides, and now we're done. So we're going to, if we do that, if we add v naught squared to both sides, we get v squared equals v naught squared plus 2a delta x. Right? Add this over here, and then I just write the equation in opposite order. I get that. And that's my fourth kinematic equation. Yes? Zoom in? And by the way, if you're way back there, feel free, there's a little table right here. Feel free to come to forward. Now, I'm going to summarize what we've done here. I'm going to make a list of equations. V equals V naught plus AT. That's my first kinematic equation. My second equation that I derived was the displacement, my change in position, was equal to my average velocity, v plus v naught over 2. That's my average velocity times time. This was the trapezoid thing that we did, area of a trapezoid. My third kinematic equation, well, v naught times t, that's the area of the rectangle, plus 1/2 at squared. That's the area of the triangle. This is how much I changed my position because I was already moving. And this is how much I changed my position because I'm changing the rate at which I'm moving because of acceleration. Then I add this fourth kinematic equation that I just derived, which says that v squared equals v naught squared plus 2a delta x. Now I'm going to make a chart here And you may use this chart on an equation list that you can use to take any quiz or test. I would start making an equation list now that you will be allowed to use for the rest of the year. On the final, on everything. There's only one test I give where I don't allow it, and that's to get ready for the state standards test. And I give you an equation list for that. So at first, these equations will be a little awkward, but you'll use them so much that you will memorize. You'll end up memorizing them. So, what's missing from equation 1? Delta x. No! Yes, yes, yes. What's missing from equation 2? Acceleration. Yes. No. Yes, yes. What's missing from equation 3? Final velocity. Yes, yes. No. Yes. And what's missing from the 4th equation? Well, I substituted for time. Yeah, remember I did that little algebraic substitution to get rid of time. So time is in 1, 2, 3, but no, it's not in 4. Now what's in all of them? Phenon. Yes, 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 yes. You have to know your starting velocity. I'll always give it to you, or you'll have enough to solve for it in one of these equations. Okay. Also remember that this is delta x. Here, here, and here. And delta x, you can think of delta x as really being your final minus your initial position. And so if you want to know your final position, you will also need to know what your initial position is. But usually, they're just asking for a displacement. Now, this gives me a little chart that when I am given a problem with constant acceleration, I've got this list of equations that I can use to solve the problem. And I actually call it shopping for an equation. All right, so if you like to shop, you'll enjoy this. Because many problems involve something like this, okay? And so I'm just going to write this as an example problem. A car starts from rest and accelerates at a rate of 3 meters per second squared, or meters per second every second, for 10 seconds. A, how fast is the car moving at 10 seconds? B, how far did the car travel? So this is a typical textbook kind of problem. Okay, and you're going to have to know how to solve these kind of problems. So here's how I want you to do this. When you're doing the textbook problems or the problems on the worksheet I'm about to give you, you don't need to copy down the problem like this. Okay, so let's suppose this is what you read. Here's what you do. Given. Write out the whole word. Don't just put a capital G. Write out the whole word, okay? Now, you read the problem carefully, And there are clues about, I mean, well, they tell you what's given, but you have to put them in terms of these variables. So a car starts from rest. Now, what is it telling you if the car is starting from rest? My starting velocity is equal to 0. So it doesn't say our starting velocity is 0. It says we start from rest. So that's one of those keywords you look for. And accelerates at a rate of 3 meters per second every second. So the acceleration is 3 meters per second every second. I like to write it like that. I go back and forth. Now, what's my final time? 10 seconds. Now, I usually like to draw this around a picture, although this is a pretty simple problem. So I show my little car right here. Put a little spoiler on it if it helps, you know. Okay. And you could write this all around here, and we want to know, I mean, what are we trying to find? For part A, what are we trying to find? How fast is the car moving at 10 seconds? So what is that? What variable is that? It's v, right? Our final velocity. And then for part B, how far did the car travel? What's the variable we use to represent that? Delta x. So if I was to draw a picture of it, I could say, okay, v naught equals 0. I'm going to accelerate at 3 meters per second squared. I'm going to go a certain delta x. And here's my car. You know, at the end, it changed shape. I don't know why. Okay, and here's its final velocity. And so now we're ready to solve. So write out given, write out what you're trying to find, and solve. Now, what I do, and this is pretty easy, but I look at this and I say, all right, I know my initial velocity, I know my acceleration, and I know my time. I don't know delta x. There's no delta x given. That's a little hint. No delta x given, and I'm trying to find velocity. Delta x, no delta x given. Boom, I'm going to use that equation. So I use the first kinematic equation for part A. Okay, now I want you to write down the equation before you plug in the numbers. You will get more partial credit on a test if you do that. If you make a mistake, I'm going to try and help you by awarding you partial credit, right? But if you don't show me what you're trying to do, you just start plugging numbers in, it drives me crazy, all right? I'm not going to give you the points. So V equals, now I can do this. This is 0, so it's just A times T, 3 meters per second every second. We're going to do that for 10 seconds. Cross off your units. And I'm left with 3 times 10 is 30. 30 meters per second. Box your answer, please. Now, part B. Well, look what I've got. I'm trying to find delta x, and I'm given V naught, A, and T. There's no final velocity given. No final velocity given. No final velocity given. I'm going to use equation 3. And then I plug in my numbers. Delta x equals, now what's V naught? V naught is 0, so I just kind of go 0. It just goes away. And then I have 1/2 3 meters per, now actually, I'll go ahead, I'll show you why. I kind of go back and forth between meters per second every second. 3 meters per second squared times 10 seconds squared. So delta x, my displacement is going to be, well, what's 10 times 10 is 100. Divided by 2 is 50. 50 times 3 is 150. Okay, that's how I do it without a calculator. This gives me seconds squared, though, right? You square the number, but you're also squaring the units. So 10 seconds times 10 seconds is 100 seconds squared. So this second squared will cancel the second squared there, leaving just meters. And there we go. Now, this procedure for problem solving is very powerful, using give and find and solve and understand. Yes? Question? Okay, the question is, why did I cross out time here? Well, it is 10 seconds, right? The time is 10 seconds. But what is 10 seconds times 0 initial velocity? It's 0. The whole term is 0. You're correct. The time is not 0. This time, t, is not 0. But I'm multiplying it by something that is 0. So therefore, the whole term goes away. It's 0. Does that answer your question? Okay, very good. So, look, I hope that many of you go on and study engineering in college or something like engineering. If you do, you're going to work billions of problems like this. Well, not billions, but you're going to work a whole lot of problems very similar to this. And setting up the problem very carefully, identifying what you know, what you're trying to find in terms of the variables we use, picking out the proper equation based on the assumptions that are being made and, you know, based on what we know, and then showing units, laying it out nice and neat and you know, methodical. You are going to have such an advantage. Okay? This is good stuff. I want you to do it this way. This is how I was taught at Cal Poly San Luis Obispo. Okay? When I was an engineering major there, I have friends who are working engineers who have to solve problems. And they are so well trained at doing something very similar to this, where you very carefully lay out what are you given, what do you know, what are you trying to find, and then going through a very methodical process of solving those problems. It's really, really, really good. So this is how I want you to solve the problems on the worksheet I'm about to give you.